Okay, so new topic for today. So we're into chapter 15 now. Things are about to get very different. We're going to be studying some new kinds of integrals. They have a lot in common with the kinds of integrals that we've looked at up to now, in that they are still chop it up, add it up. And that's the fundamental point of view on integrals that I want you all to retain. You know, if you retain only a couple of snippets of concept from this course 10 years from now, right? I want one of those snippets, one of those, single frame images in your mind that you take from this class to be that what an integral fundamentally is a Riemann sum, but the way you think about that is chop it up, add it up, right? Take a domain that's related to some problem that you're interested in. You're computing some accumulating quantity, whatever that is. You're going to take that domain, chop it up into pieces. On each little piece, the problem becomes easy. You write down the answer to the question as it pertains to each little piece, and then you add up over all the pieces, right? So this is the fundamental idea behind a Riemann sum, with a lot of details, of course. Different in every context, of course. Computational methods, yeah, right. But deep down, fundamentally, chop it up, add it up. Right? So one of the big takeaways. So, we're going to be seeing a different kind of chop it up, add it up construction. And then we're also going to see, and so the really exciting thing about chapter 15 is some really unexpected relationships between different kinds of integrals in ways that we really have not seen in chapter 14 at all. So one of the big differences in chapter 15 is what the integrand is. What kind of an object are we looking at? Integral of what? And, what are we computing? The new kind of integrand for the chapter 15 integrals is a new object, something called a vector field. So before I can get into the chapter 15 integrals, I've got to tell you what a vector field is. And here we go. A couple of examples just to kind of, so you have the right picture in your mind. Like this. Now, what do these represent physically? We'll get to that soon. A couple of minutes. But first, I just want to talk about, what these things are, how you represent them algebraically, and fundamentally, here's the way I want you to think about vector fields. A vector field is a way of associating to every point in Rn. For example, maybe here are some points in the xy plane. Here are some points in R3, XYZ space. To every point, you want to associate a corresponding vector. Now, remember, points and vectors, though they pair up in a sort of a canonical group, you can sort of think of one as the other, you can conflate them, you can sort of ignore the differences. But they are, in fact, different things, right? Points are locations, vectors are a harder thing to talk about, right? They're a direction combined with a magnitude, you might think of it as. You might think of them as representing displacements or velocities or forces, but it's a fundamentally different thing. And so for each of these points, we associate a corresponding vector. And I appeal to your geometric intuition. If I were to fill in this diagram that I've drawn here, if for every point I were to have an associated vector represented by an arrow, as of course we do, then you'd get an interesting looking little mathematical object. It'd be hard to draw a full picture of that. It gets ridiculous at some point if I were to draw every single point and every single associated arrow. The picture would just be solid black, right? So we can't really draw the full picture, but nevertheless, you can imagine there being a full, fully filled in picture representing something. We'll talk about, again, physically what that is coming up soon. Okay. So, how do we write this down algebraically? I want to think of this as a function. The big idea is, again, at every point, so for example, this point, for every element of Rn thought of as a point, I want to have an associated vector, again represented as an arrow. And if you think about it, that's what a function is. A function says for every input I get an output. It's just that here the inputs are thought of as locations and the outputs are thought of as vectors. All right. All right, now, for example, what do these functions look like? Here's a nice for example. I claim this function might look something like that. Now, again, let me just plug in some actual points, see what we get. So, for a point, x comma y, maybe 1 comma 2. That's a point in the domain, right? The associated field vector, I guess I'll do this in green. The field vector, the value of the vector field. Okay, well, by the way, you can take x equals 1, y equals 2, plug into this formula. Out comes this, this y minus 2x, comma x plus 1. You get actual numbers there. Happens to be 0, comma 2, which we interpret as a vector, which we draw as an arrow. Okay, so notice that's what this function does. This formula that I wrote down actually achieves what we were talking about. You give me a point, I give you an associated arrow. Okay. All right. Now I just plugged in a single point here, right? I mean, obviously there's infinitely many points here. It's not just this one point. There's infinitely many points. And if every single point in the domain I were to plug into this formula, I'd get correspondingly many arrows, and my picture would be uninterpretable. Right? So we typically, again, only draw a handful, what you might think of as a representative collection of points and arrows. Just enough to get an idea of what does this thing kind of look like, but not enough to make the picture cluttered. Okay. I want to make a point before we go on. These pictures that we're drawing, these are not graphs. Y'all remember one of my little pet peeve, right? Soapbox, sore points, right? Is you got to be careful with the word graph. Graph means something very specific. Graph is not interchangeable with the word picture or figure, right? So graph is a specific, precisely defined construction whereby a function creates a picture. It does not mean just any old picture. So this picture that we're drawing here, it's not a graph of the vector field. It's also not a level set. It's also not an image. I mean, if you just think through, all the kinds of pictures that we know how to draw, this isn't any of those things. It's also not this other picture that we've drawn on some occasions. You remember this one where we draw the domain over here and we draw the target over here, and that's a really useful point of view if you want to think about how do input changes cause output changes. We drew that kind of, domain target picture. We drew that a lot in chapter 13. We drew it a lot when we were doing change of variables. Right? So let's enumerate the number of things that these pictures are not. They're not graphs. They're not level sets. They're not images, aka parameterizations. They are not domain target kind of pictures. This is picture number 5. This is geometric construction number 5, right? In the course. So anyway, make sure not to be sloppy about again, it's a huge problem in, for students taking this course is to algebras mean pictures. Right? And you gotta remember there's so many different ways that, depending on the circumstance, we need in so many different ways to relate algebra to pictures. So this is a different one. Okay, some examples. Let's look at that vector field there. For every point, we have a formula for the corresponding field vector. The corresponding field vector given by this formula. The field vector is an easy formula, right? It's just 2, 1. So for every one of these points, I draw the corresponding arrow, 2, 1. And so you can see for this kind of a formula, that's the kind of picture we get. So that is what you might call a constant vector field. Notice it does not look like a graph of a constant function. This is what it looks like very differently when we draw this vector field picture. Okay. Here's another seemingly easy formula. Let's make sure we understand what this simple little formula looks like. This is the formula that says that for every point, for example, there's a point. For every point, the field vector the field vector created by this function is the same as the position vector for that point, right? So xy is xy. The position vector for the point is that. So when we say that the field vector is the same as the position vector, what we're saying is that that's the associated field vector, right? So now, of course, we always draw field vectors with their tail at the point. That's our convention. That's our, it's how we draw these pictures. Position vectors of the point itself are kind of the other way, emanating out of the origin. But anyway, the punchline is this is what that picture looks like. So this f of x comma y equals x comma y is a field that's sort of, if you will, emanating out of the origin. It's like rays away from pointing away from the origin. We'll talk different ways about this at different times. Okay. Here's another example, and this one's just kind of, it works out curiously. This is a weird one. F of xy is negative y comma x. What does that look like? Look, you could plot a bunch of points. That's fine. But sometimes you get lucky, and there's a convenient relationship you can notice. Notice that these two vectors, namely the location vector and the corresponding field vector, notice that they have the same magnitudes. That's cool, right? How about that? And furthermore, they're always orthogonal to each other, right? Just check it out. Dot product's clearly 0. Therefore, they're orthogonal. And with that information, that pretty strongly motivates this picture. For every point, you look at the position vector for that point. The field vector is same magnitude and perpendicular. And that, well, it just kind of suggests a picture that looks kind of like that. Now, at confession, it could have been something, slightly different. I mean, how do I know that the vector didn't point, that way? That would be perpendicular and of the same magnitude as well. Well, plug in a couple of points and just notice, right? So you plug in any short list of points and you can immediately see, does this, swirl? You might think of this as a swirl. Does that swirl go clockwise or counterclockwise? Well, like I say, just pick a point and by inspection. This one happens to go counterclockwise. Yeah?
Is this what the vector field looks like? Like, because of these observations, this is what all vector fields look like?
No, this is what this one specific vector field happens to look like. So it is only this vector field. Oh man, I just circled in the wrong color. It is only this vector field that has this property. Oh, correction. We're only observing for this one specific vector field that these properties are satisfied. Okay. Of course, it's pretty easy to notice in the case of these vector fields, it's clearly not. Yeah, so this is a highly specific observation. Yeah. Okay. There's a special kind of vector field. What's special about this vector field we'll see later on. For the moment, I just want to make the observation that this is a vector field, and I want to make a kind of a geometric association with it. But anyway, gradient field. So now this might seem a little weird. We've already talked about gradients. Why are we talking about gradients again? We already know some things about gradients. Reminder, we know you can use gradients to compute directional derivatives. We know how gradients have a geometric interpretation. They point, in the direction of fastest increase. Or they point uphill on the graph, however you want to think about it. But we never thought of them as being vector fields. Up to now, we've thought of the gradient as just being a vector. Right? It's the formula for it. It's a vector. Right? But what we never sort of really broadened our point of view on at that time was it's a vector at each point. Right? So we always focused our attention on a single point in Rn. But if we think about how, as a function of location, depending on where you are, you get a different vector. It depends on the point, right? Well, that's a vector field. And easy formula. There you go, right? So there's your formula for your vector field, what we call a gradient field. And specifically, at every point, there is a corresponding vector. And in chapter 13, all we did is just think of, okay, at a certain point A comma B, then the gradient is a vector, and we think of how that vector allows us to do certain things. Okay. So just to help you relate our chapter 13 observations with our now current observations of thinking of the gradient as a vector field, let's take a look at this picture. We already know a lot about this function. That function, I can draw the graph. The graph looks like that. Old news. Right, the graph you get by setting f equal to z equals x squared plus y squared. That was our first paraboloid, so we know that's the graph. This gradient field, we can draw this picture of it. Now, again, how do you know that? Well, you look at the formula, notice that the gradient field, the field vector here is just 2 times the position vector, and I did not represent this artistically very well, but, so at a point like that, the field vector is twice the position vector. So that's supposed to be twice the position vector, and I didn't do a good job at other points. Sorry. But anyway, you can see it's another one of these sort of radially outward kinds of things. And now let me just combine these pictures and notice that, you view this function, think about its gradient field, smash these pictures together, and as, we already understood, notice that these gradient vectors, let me say that differently, these vectors in the gradient field in the domain, they do always point uphill on the graph. Right? I mean, think about how paraboloids work. If you're on a paraboloid surface, uphill is always radially outward away from the origin. So that tracks, right? All right. Again, why gradient fields are other than sort of, oh, hey, check it out, we've already seen this before. The other reasons that gradient fields are interesting or it's a long conversation. It's gonna come up over. Gosh, it's gonna take most of the rest of the course for us to really flesh out why gradient fields are particularly interesting. We're gonna see a glimpse of this in a few minutes, but again, fully fleshing it out is gonna take some time. So I request your patience on that. Okay, so we've spent several pages here talking about, what do vector fields look like and how do we represent them algebraically. And now let me go to something that you might have been thinking about all along, namely, what does this have to do with the real world? Right? Is this just a sort of a mathematical sort of, game? What do these represent physically? So there's a lot of things that vector fields can represent physically. I'm going to show you what I'm going to call the 2 big ones, and that's a subjective statement. But anyway, here 2 big ones anyway. Y'all have probably heard about gravitational fields. You hear about that in physics classes. You hear about it in science fiction movies. Right? So, what is a gravitational field? Is it a real thing? Is it kind of like a force field, like in Star Wars and stuff? Is it a real thing? Well, actually, in fact, it's obviously gravity's real. But gravitational fields, this term, this construction, gravitational field, is a totally real thing. And furthermore, it's a very natural little grammatical construction. Because a gravitational field is just a matter of observing how the formula for gravity, that's the formula for gravity. If you give me a point, x, and if at that point you plug into this formula and make the corresponding vector, right? Gravity pulls toward the center of the mass. It pulls toward where, what's applying the gravitational field. You get a vector field. So the term gravitational field it's kind of a shortened version of the vector field defined by gravity. Extremely natural, right? So vector fields, the first example that I'm going to give you of a vector field is, in terms of something physical, vector fields are the natural way to represent how gravity actually works in the real world. So how's that for natural? Right? That's extremely natural. It's extremely applicable. It's extremely useful. This thing that keeps us from flying off into space, right? How handy is that? Is a vector field. How are we doing? Is everybody on board? Okay. Here's a neat fact, by the way. A lot of people don't realize this. This is an underappreciated point, I think. But look at the formula for gravity. And now look at the formula for the electric force. Oh, this is called the electric force when you talk about it in a high school class. But this is a vector field, right? That is described by electric forces. So they call this, of course, the electric field. So check out these formulas. Notice how structurally these formulas look exactly the same, right? These are radial vector fields that have magnitude of x cubed in the denominator, and other than that, everything else in the formula is a bunch of constants. Structurally, these look exactly the same. Right? And it's a big deal. So later in the course, by the way, we're going to spend a bunch of time talking about gravitational fields and electric fields. I'm going to spend most of our time talking about gravitational fields because I feel like gravitational fields are relatable. Right? Your intuition for how gravity works. This thing that again you deal with or battle against every day. Right? That is the perfect metaphor for understanding electric fields, and those of you who are engineers are going to, I hope this is no surprise, I hope, going to have to know a lot about electric fields. Because that's how electricity works. And electricity is how your iPhone works. So this is important, right? For lots of things that you do in engineering. So think of gravitational fields as the perfect metaphor for understanding what you're really going to care about later on. Okay. Okay, now here's another example. Here's another physical example of electric fields, and it's what I'm going to call flow fields. Fluids. For example, so, how does air move in space? We're inside of one of those right now, right? There's a fluid called air in this room. I hear the air conditioning, it's on. So there's a certain amount of airflow. Some of y'all are probably right under the vent getting cold air blown on you, right? So there is a flow of air it's invisible, of course, but there's a flow of air in the room right now. How would you describe the way air flows? At every point, at every location, right? So right there, for example, the air is moving in a certain direction and with a certain velocity. Namely, you're going to describe the flow of air at this point with a vector. For every point, you get a vector. Vector fields, the perfect tool for describing how fluids flow. Right? So, and there's lots of other examples of fluids flowing. I mean, how does water flow around in the ocean? What's an ocean current? How do you describe ocean currents? Well, it's with vector fields. Right? How is pollution or other contaminants, how's that flowing around in the ocean or in the atmosphere? Other components of the atmosphere, how's the ozone moving around? It's stuff like that. Vector fields are the perfect tool for describing these things. That's in R3, of course. Now, what about an R2? Why do we need to talk about R2? We don't live in R2. We live in three-dimensional space, right? But in a way, we kind of live in R2 because we live mostly on the surface of the Earth. Right? So I'll say this, if we ignore altitude and just want to understand how do things move around, how do their projections onto the surface of the Earth move around, that's still pretty darn interesting. Right? If you're interested in animal migrations, we don't need to keep track of how much the buffaloes are moving up or down. That's not really you know what I'm saying? They don't do a lot of that. Right? Every so they sit down, stand up, So it's mostly an R2 thing. Likewise, how does water flow? Right? Pollution, pollen, things that you mostly want to keep track of where they're on the map. Not so much about the ups and downs. Okay. So there are tons of fluids whose flows are interesting, and we describe those with vector fields. And my term to describe this particular metaphor for vector fields is flow fields. Okay, so there's two broad stroke kinds of vector fields that we're going to talk about. What I call force fields, again, not in the Star Wars sense of the word, but vector fields representing forces. And then separately, completely different physical metaphor, vector fields used to represent flows of fluids. Okay. And I want to point out that both of these are important. Both of these are really important, not just because of the applications, but because visualizing vector fields in these different ways give us different abilities to interpret mathematical constructions that we're going to make. There are some constructions that we're going to talk about. There is some math that we're going to study in this course where you really need to be able to view this vector field as representing forces. You can't really make sense out of without interpreting this as forces. On the other hand, there are other mathematical constructions we're going to talk about in this course that you really can't make much sense out of without interpreting this vector field, same vector field, as representing a fluid, flow of a fluid. Right? And of course, those are very, very different things. Right? So thinking of this as a fluid conjures a certain kind of a picture. Thinking this as representing forces conjures a very different kind of a picture. So don't make the mistake. A lot of students make the following mistake, which is to say, between these two choices, I'm going to pick one, right? I'm going to pick this one, and I'm going to ignore this one, and I shall think of everything in this course as, my physical metaphor shall always be forces. That's a huge mistake. You can't do that. You got to be able to think of the vector fields in both senses. Both are critical. How are we doing so far? Is everybody on board? Okay, the book makes a choice at this point that it's not what I would have done exactly. It's not what I did. But anyway, whatever. Partly to be consistent with the book's choice, I'm going to go ahead and do what the book does, and I'm going to introduce a bunch of operators. So operators are things that you can do to vector fields to get other things. So as the book does, here they are. There's this thing called Green's operator. There's the formula for it. There's this thing called divergence of a two-dimensional vector field. There's the formula for it. There's this thing called curl. There's the formula for it. There's this thing called divergence in a three-dimensional vector field. There's the formula for it. Hard to follow, isn't it? Right. There's a bunch of formulas that I'm asserting that these are important, and I'm giving you no context, no reason to believe other than whatever trust you might have in me, right? And in the book. I'm giving you no actual persuasive reason to believe that these are actually interesting. So it's an uncomfortable choice to just kind of throw these formulas out there. But anyway, the book does, so I'm going to do it too. Give me 2 seconds. So what I'm going to suggest to you here is, and I am going to, while we're here, make a couple of neat points, things to look out for. But mostly all I'm going to say here is keep your eyes open as we go through the course, the rest of the course, for these operators that do have natural geometric interpretations and also natural physical interpretations. So just at this moment, kind of be on the lookout. For the moment, they're just formulas, right? Don't feel like you've learned something because you memorized the formula for Green's operator. Symbols on a page at this point. Yeah, you had a question.
When do we, and this might be part of the interpretation, but when do we know those, use which one?
Oh yeah, that's a long, detailed, conceptual conversation that we're going to have over the next several weeks. Yeah, absolutely. So for the moment, like I say, it's a weird. I think it's weird that the book introduces these things and then gives you no context for them. Right. Oh well. Okay. Apologies for that. So I am going to introduce a little bit of notation. This is kind of neato. Y'all remember we've talked about the gradient previously. By the way, the gradient is another operator. The gradient is something you can do to a function and get another thing out of it. So you recall that we write gradient as, let me write it over here. We write gradient f equals, and then we, of course, we take the x partial of f, and we take the y partial of f, and we take the z partial of f. And now, as is kind of vaguely suggested by this notation, let's view that symbol as being these things that I'm clearly doing to f. Now, this is just notational kind of suggestion, right? I mean, this is there's something a little bogus about this. I mean, we write this little triangle symbol equals and then a vector consisting of partial derivatives. That's not really a vector, right? A vector has a direction. What direction does that point? Right? That's not really a vector. Right? So it's notational convenience. Right? That said, it's a pretty natural, it's notationally natural convenience. And it's extremely common. Everybody does it, and it actually is, it's a great choice for the convenience of it all. But just don't make the mistake of thinking that that's actually a vector. Right? Anyway, with that suggestion having been made, let's just kind of think it through. If you take that, air quotes, vector, and if you were to dot it with some vector field, F, with components PQR, notice what you get, weirdly enough. This thing that you get, it's exactly that. You get divergence. I mean, just again, kind of think it through. You take the x partial of the first component of f, you take the y partial of the second component of f, the z partial of the third component of f, and there it is. There's the exact formula for what we've previously, again, mysteriously and with no context, what I've previously written as divergence. So because of that kind of notational coincidence, very often people will write divergence as what we call del dot. Okay, so the way and again, this is just semantics, but the way we pronounce this symbol is del. Please don't say gradient. Gradient is what you get when you apply the del operator to a function. I wanted a color change. So this is gradient. Right? That little triangle by itself is del, not gradient. Gradient means you're doing a certain thing with del. Does everybody see the distinction? So be careful with that. So again, back to divergence, we will pronounce very often del dot f. And it's a notational convenience. It is extremely common. It is especially common in applied sciences. So for example, again, I call back very often to my ye old days as a second major in physics. In my physics classes, I saw del dot far more often than I saw div. Right? So it's a very common notation. I sort of assume in engineering it's probably comparably common. So you definitely have to know. And because of that, I actually use del dot actually more often than I use div also. So heads up for that. So analogously, and I'm going to let you guys think through the details of this one, curl. Coming back up here, this thing called curl. If you just write it out and interpret it naively, curl is very naturally written as del cross f. Just kind of write it down as if it makes sense. Kind of like symbolic determinants. We use symbolic determinants to compute cross products. Y'all remember that? If you likewise write down symbolically the nonsense of what it would mean to take del cross f, you get exactly the same as the formula for curl. Super weird. So again, very common. And again, I'll be using this notation a lot. Del cross means curl. Okay. Yep.
What's the physical meaning of del?
Oh yeah, that's not. Yeah, this is a mathematical abstraction, and it's a notational convenience. But yeah, I can't draw a picture of it, and there's no physical example of that. Yeah.
Okay. Can you also explain very quickly or remind me about like what's the physical meaning of gradient?
Yeah, that'd be a great question for office hours. Let's talk about that in office hours. Yeah, right. Okay. Okay, so here's another. Again, while we're here. Oh, I'm sorry. You had a question.
Sorry. Does that mean del cross f is also equal to what curl of f is at the, like under the operators?
Yeah. No, that is what I'm saying. So in other words, if you write this down, interpret it in the only plausible way, what you will find is that you get that as a result. At which point you're like, oh my God, check it out. That's exactly curl. Okay. Yeah. And that's a nice, healthy little exercise. I mean, actually write that down as a symbolic determinant, and crank it out, and you're going to be like, whoa, what are the odds? Okay, so again, while I'm here, and again with full apologies, I know I've given you no geometric context for why we should care about any of these operators. And it gives me the willies. But I'm sort of, pigeonholed into this by the fact that the book writes these down here, and there's exercises that are about this, so I kind of have to do it. While we're here, I mean, one thing that, again, a little bit of foreshadowing. These operators, you're going to notice this as we go through the rest of the discussion of Chapter 15, which is most of the rest of the course. These operators, heads up, they kind of relate to each other in some very natural ways. So you just be on the lookout for this. But it's going to make sense. We'll see it play out. It's going to make sense to kind of, because the square peg fits into the square hole, it's going to make sense to compose the gradient operator with Green's operator. I mean, just, in R2, check it out. If you have a function, if you take its gradient, you get a vector field. Well, if you have a vector field, you can plug that into the formula for Green's operator. So again, square peg, square hole, it fits, and it turns out to make great sense to think of things this way. Why? Again, to come later. Right? There's a long discussion there. Likewise, again, everything kind of fits together if you compose grad followed by curl followed by div. And they just fit together in a really, I'm going to say coincidentally natural way. And it's not really a coincidence. There's deep reasons for it. But anyway, it's going to seem coincidental. And I will tell you one thing right now that you can already verify. It's still not even knowing what these things represent physically. There's an algebraic thing that you can observe right away, most of it anyway, and that is that these are what we call exact sequences. Roughly speaking, what that means is that everything dies after two steps, and by dies I mean becomes zero. I think this is a darkly hilarious metaphor, right? If you're multiplying by stuff, just multiplying. If you think about it, zero is a nothingness from which you can never return to somethingness, right? If you're just multiplying, you can multiply by 2, you can multiply by 7, you can multiply by 6. Things change, they become different things. But as soon as you multiply by 0, I don't really care what else you multiply by after that. You remain 0, right? So it's kind of like death. Anyway, I just am endlessly amused by that, but I have a dark sense of humor. Anyway, everything dies after 2 steps, and you can see that happening here. Where what would it mean for this? For everything to die after 2 steps here, it means that if you take a function and if you compute its gradient, and if you then subsequently compute Green's operator of that gradient of that function, you will always get 0. So this is, in this context, everything dies after 2 steps means this, and you can totally compute that right now. Now again, not knowing what this means geometrically, how does this relate to anything physically? Oh, yeah, we'll get there, right? But How about that? That's a little bit of an eyebrow raiser already. Right? Algebraically, wow, those fit together. Yeah. It's a little bit harder to check, but you can still technically do this. If you have a vector field into which I got my grammar backwards. If you have a vector field that you plug into Green's operator, if you get 0, then there is a function for which that vector field is the gradient. And so this death here, right, came from a birth, if you will, over here. So it did not die after one step, even though you first observed it after just, from here. But it actually came from over here. And so 2 steps. Here it is. 2 steps. So it's a weird thing that this is true, but 2 steps. And this is, I'll get right to you in a second. Turns out, hard to explain in this context, but the fact that everything, there's a little asterisk, I don't want to get into the weeds about the asterisk, but the fact that everything dies after 2 steps is a consequence, fundamentally a consequence of the geometry of space. It really is. It's about fundamentally about the geometry of space. And if you're curious about that, come talk to me in office hours. It's a long and deep conversation, but I can hit the highlights for you. Yeah.
So you said after 2 steps, if you get 0, then there's a function for the gradient vector?
Yeah, in any one of these diagrams, if you have some thing, right, and if you apply the appropriate operator per the context, and if you get 0, that means that there is something that makes that. So everything has a lifetime of 2. And so if you die here, then you were born here. Yeah, it's and again, everything, there's an asterisk, and there are micro exceptions, but So again, the reason I'm telling you this now is one, to just be kind of again get the eyebrow raiser, right? I want y'all to be like, whoa, maybe these are algebraically natural. Maybe these are not just arbitrary formulas that are just kind of written down, right? Maybe there's something going on here because that's pretty weird, right? And the other is that this gives you something to be on the lookout for. I'm a big believer, just sort of pedagogically, that if you sort of know what patterns are going to emerge, and if you're on the lookout for them, then as they emerge, you'll be more able to see and retain them, right? So heads up for this weirdness. It's going to be a big part of what we talk about through the rest of the course. Okay, I wish the book did more of this. Okay, so heads up. By the way, there are other analogies, there's other connections and comparisons between these operators. I'm going to make a big deal out of these as we go through the rest of the course as well, but nevertheless, be on the lookout. Okay. All right, so moving along. We're going to talk about line integrals. We kind of already did. Let me go back real quick. Y'all remember a while ago we were talking about, what happens if you're doing a chop it up, add it up on a dimensionally awkward domain, right? We wrote down 2 new kinds of Riemann sums, aka integrals. And we spent a bunch of time talking about surface integrals because, again, that's the choice that the book makes. And they like to do 2 dimensions before 1 dimension. I'm not really sure why, but whatever. It's their book. And remember that I kind of segued into that by starting off with a discussion about how, one-dimensionally, curves and little pieces of length, how can you actually view those in a pullback context? And here it was, the very next page that we did. We look at a curve, we view it as an image of something simpler, and then we did this whole pullback argument. We understand this piece of curve by virtue of this position differential, vector differential, which we understand in terms of its components. And once you understand its components, then you understand the vector, And then from that, you understand that little piece of length that you were interested in, right? If you want to compute mass, mass is mass per unit length times length. There's the length. Okay, so we've already developed all of that. Here we go. And so just a quick reminder, here it is. So that little piece of length, again, understood by the position differential, which is understood by its components, blah, 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 and here's our formula for ds. Related, given that that's our formula for ds, we identified this stretching factor, that stretching factor being how we rewrite ds into our pullback. Okay, so that's all. We did that already for segue purposes a while ago. Now I just want to show you some applications of this then. And I'm going to go super quick through this because this is very pluggy-chuggy. Honestly, it's not that different from surface integrals. It's just easier. This is a one-dimensional version of surface integrals. And the parameterization tells all. So our domain is parameterized. There's the big question of how do you get the parameterization, right? Fine, okay, but the parameterization allows you to do everything. And so, for example, suppose you want to compute a mass. Well, a mass is a chop it up, add it up problem, namely a Riemann sum, namely a line integral. ds is VDT, straight out of our formula. Right now, we computed the stretching factor. Right, so that's how you compute your stretching factor. But ds is stretching factor times dt. And of course, knowing what that is, right? Knowing that our stretching factor is what I have circled in yellow here. This becomes that. And everything else is pretty much plug in, right? So delta, our density, is x plus y. How do I deal with this x plus y? Well, don't forget, x and y are given to you in the parameterization, right? So let's see here. So this x is t. It is very pluggy-chuggy, right? Everybody see what's going on here? It's just like we did for surface integrals, but just easier. No cross products. Likewise, y. Again, totally given to you by the parameterization. Suppose you're not computing mass. Suppose you're computing centroid. Okay, well, then we have a slightly different integral. We have a slightly different integrand, x, for the same reasons, given to you by the parameterization. Everything else is the same. Okay, so I don't want to spend a bunch of time on these examples. Again, I think they're very pluggy-chuggy. It's just a matter of remembering how do applications come from Riemann sums, and then how do we pull back to compute the Riemann sum. Okay. Here's another example. This is not terribly different, and I'll be real quick with this one, but I think this is a good example. Hypothetical. Suppose you're trying to build a fence, and this fence is going to go around your plot of land, and for reasons that are let's not worry about why, but you have a formula for height as a function of where you are. You want the fence to be higher over on one side and lower on the other side. Maybe it's because of the shade that you need for your garden, or privacy that you need from a nosy neighbor, or you just think it looks cool, whatever, right? Notice what we're doing is for each little piece of a curve, ds, we are multiplying by a height to get a little piece of area. So we are doing a chop it up, add it up. The total area of this fence is the sum of the areas of all the pickets. Okay? Each picket has area that's height times ds. And so altogether, you're computing... Oh, I forgot my color scheme. You are computing a scalar line integral. And, parameterize, pull back, plug, and chug. Right? ds, don't forget, is v dt. That v, the stretching factor, you look at the parameterization, that stretching factor happens to be 1, and you get a pullback integral. Okay. All right, so y'all can look at the rest of the details of that one. Call it right here. Y'all have a nice weekend. See you later. Oh, and hey, while we're here, don't forget we have an exam next week. Right? In case you had forgotten. See y'all later.